Thank you. Oh, except their faces. Don't get their faces. I don't know. I don't care. Whatever. It doesn't matter. What's a valence electron? What does valence mean?
I know what it does, but I don't know what it means.
That's fair. What does it do?
So basically, well, in the analogy that the Mr. Anderson gave us, it's like they're in the electrons that give a like positive charge that are like parking spots on the outer areas of the nucleus.
That word that you said, the outer, that if we Google recipes, if we Google valence electrons, it says a valence electron is an outer shell electron that's associated with an atom. So that it's that outer shell place where we find electrons. If you think about it, if the nucleus is, the nucleus has a positive charge and you've got electrons around, the further the electrons want to be by the nucleus, right? The positive likes the negative, but they're spread out, and the further apart they are, the higher energy. So in order to pull the negative thing away from the positive thing, that takes energy. So the farther they are from the nucleus, the more energy had to be added to them to get them up there. So the valence electrons are the this is hard to do. Okay, so the valence electrons are the highest energy electrons. So they're the furthest from the nucleus, way out there. And these are the ones that tend to participate in chemical reactions. So that's just kind of the basics of what the heck electrons are. And then when you go to start looking at equations and trying to figure out what they mean, there's some stuff you got to know. Everything on the left-hand side of the arrow, these are the reactants. So these are what we're putting together, kind of like your ingredients. Like if you're going to make banana bread, you have to get your flour and your eggs and your baking soda and all that stuff. So those are the reactants. Is my handwriting really messy, Lisa? Is it causing you grief?
I just didn't know if after the N it was a Z or a 2 because it's very.
Yep.
Yeah.
Yep. Those are 2s. I will always cross my Z's. So a Z will be like this and a 2 will be like that. That's what I've figured out. That works for me and the way I write. Yeah. So our reactants are on the left-hand side of the arrow, and then on the right-hand side of the arrow, those are our products. And products are what we produce. So reactants are what we put in, and products are what are produced. And then this weird little symbol here, this symbol, you could sort of blow it up and make it like an arrow going to the right and an arrow going to the left. The idea is that you've got something, you've got your reactants making your products at the same time that your products are making your reactants. So it's a symbol that means equilibrium. It means that you have both reactions happening at the same time. So you've got the NH, or you've got the N2 and the H2 coming together to form the 2 NH3s at the same time that you have NH3s breaking down to make your N2 and your 3 H2s. So it's happening simultaneously. It's all at the same time. And we will talk more about equilibrium a little before the end of the term. We'll get into equilibrium a little bit more, but that's what that arrow means. So the rest of this equation, if we're going to read this N here, what the heck does that mean and how do we know? Any ideas? Totally fair. Okay, let's go down here to the bottom. I threw a periodic table on here. I strongly encourage you to find yourself a periodic table, whether you have one from the back of a middle school planner or if you're okay just pulling it up maybe on your phone next to you or on your Chromebook, you're going to need a periodic table. If you would like me to mail you one, let me know and I will print some out and I will throw them in the mail. And that way you can have one. I think it's really hard to do chemistry without a periodic table that you can write on. So we were looking for N. N is right over here on the periodic table. So that the N is a symbol that stands for nitrogen. Okay, and then the H is a symbol. Oh, look, this is in a different language, you guys. That's so funny. Look at the hydrogen in English, we write it like this. And if you look at the periodic table on here, it has sodium as natrium. It's funny. I wonder what language this periodic table's in. You saw that. Thanks, Eli. I had no idea. I didn't pay attention to that. That's hilarious. Zinc is, look at that, sink. I like it. I wonder what language. Anyway, okay, doesn't matter. The chemicals, the symbols are the same. Okay, so when we're up here, the N, the big capital letter, those are the chemical symbols. Okay, so you're gonna have some, it's always at least one capital letter. And if there are two letters for a symbol, like for sodium, it's Na. The A is always lowercase, it's never uppercase. So the first letter is capitalized, the second letter isn't. So if you have CO, that's cobalt. If you have, whoa, nope, not that. If you have capital C, capital O, that's one carbon and one oxygen. So you have to be really careful whether you're capitalizing things or not, because they mean completely different things. Like this is a transition metal and this is two non-metals. This one is a gas at room temperature, this is a solid, this one's a solid. Like it's very different. It doesn't look different, and if you don't know chemistry, if you don't read chemistry, you don't know that they're different, but they are vastly different, and you've got to be really careful not to capitalize things that aren't capitalized in what I give you. So over here, you've got an H, that's for hydrogen. So that's what the symbol means. Ooh, I just realized I forgot to teach something this morning. Anyway, this little 2 right here, what that refers to the symbol to the left. So I'm gonna write it up here where I've got a little bit more space. So on my N2, and then it has a G. So this is the chemical symbol. So that tells me what it is. This 2 right here, this is the number, not hashtag, but the number of atoms of the element to the left. So, wow, that's not a word. What am I doing? To the left. Okay, so if we have an N, we've got a 2 right here. This 2, use a different color. The 2 is referring to the N. So what that means, if I see N2, then what that really means is that I have one N and two N's. So I've got two N's right there. That's what that's telling me. And because the 2 is right down here, that means that these are bonded together. Not necessarily touching each other in the molecule, but it means that they are they're in the same molecule. So it's in the left and it's in the same molecule or the same compound. This is actually really helpful to have your camera on, Lisa, because I can tell when you're done writing so that I don't go too fast. Any questions so far? Reading the symbols.
I just was wondering in the number of atoms in the element to the left, like what does that mean exactly? I'm not sure.
Yeah. So if I have, ooh, that's gonna mess people up. The N2, so it applies to the guy to the left of it. So if I have like NO3, that means that I have 3 oxygens and only one nitrogen. So that would be N and then O, O, O. So the 3 only applies to the element that it's touching when it's a subscript like that. Does that make sense?
Yeah.
Okay. And what that would mean then is that this N and those 3 O's are all going to be bonded in a compound together. All right. Let's see. So if we look, this G right down here, anybody want to take a guess what the G means? Oh, I can't see the chat. Somebody this morning guessed, does it mean grams? That is a very fair guess. It's not, it's actually refers to the state of matter. So if it's a G, so the G in parentheses means gas. If you see an L in parentheses, that means it's a liquid. If it's an S, it's a, so hard because you have to unmute yourself. What's the S?
Solid.
Thanks, Ms. Stone. And Avery threw it in the chat, and you're right, it is solid. Here's a tricky one. Oh, wow, Annie, you got to write that correctly. The other one, why? Stop. The other one that you'll see sometimes is AQ, and that is aqueous. And that is if something is dissolved in water. And that happens. So these don't make a lot of difference for a lot of the stuff, but if what I was talking about earlier today when Chilcott was talking about the steam off of a pot of noodles, the steam is water, it's H2O, but it's in a gaseous state. It has a lot, those molecules in the steam have way more energy in them than the molecules in this water, in this glass of water, because they're a gas, and the gases, the particles have more kinetic energy. That's why. And so when we get to thermochem and we're trying to do calculations, the state of matter that your chemical is in will dictate how much energy is involved in the in any reactions that they undergo. So chemistry is, I keep talking with my husband while we're walking. There are so many little nitty-gritty details, and they matter a lot. And if you want to go on in chemistry, you have to be able to pay attention to those details. If you don't want to go on in chemistry, then you're learning how to use your brain and your problem solving, and those are really important skills, but it doesn't matter if it's a solid, liquid, or a gas if you're not going to go on and, be a thermochemist, but you should, because it's cool. I kind of want to do that. Anyway, okay. So that's so far we know what these symbols all mean. Good on us. Now, this thing out in front, this 3, is this, let's see, where can I write it? There we go, we'll go over here. So if I have 3H2, the 3 out front refers to, so this refers to the whole chemical, the whole compound. So this refers to everything. Did I spell that right?
You good?
I think I did. Good Lord, thanks, Morgan. Refers to everything to the right until you hit a symbol, until you get to like a plus or an arrow or like an equilibrium arrow. Okay, so this 3 refers to all of that. So that means that I have, so that is equal to H2 and H2 and H2. So this is sort of like if it was math, it would kind of be like we had parentheses around everything to the right. So this is a coefficient. and it tells you how many of the things touching it you have. So how many of the chemicals to the right that you have. So in this case, I have 3 H2s, which really, if you look down at the dot diagram that I've drawn for it, I have 1, 2, 3, 4, 5, 6 hydrogens down there, because the 3 times the 2 gives me 6. It's kind of tricky. Wow, and I just erased everything. Okay. So that's how to read all that. I think those are all the symbols that you need. The last thing that I want to do is talk through the actual, that's just how to read the chemicals, how to read the symbol. When I'm fully done, you're going to zoom out. Yeah, sure. I will definitely. And Avery, Ms. Stone is recording this, so I will throw it onto YouTube and put it into Zoom, or maybe Ms. Stone will, because it'll go to her computer. But yeah, we'll make sure that you have access to this. That's my plan. Okay. So if we look at, I'm asking you to look at this chart down here, and we're going to fill it in for each different type of atom in the equation above. So we're going to look and see that each N has the same number of electrons that are available to it. Spoiler alert, they do. And the pattern, now that you're done like writing down how to read this stuff, the actual work here is real short. It's fast. So if you look at the ends, we want to know how many dots are touching the ends. So if you look at this N right here, so we'll zoom way in, and I look at that N, I can see that it has 2 dots right over here, and it has 3 bonds right in there. And then this, the nitrogen that's next to it also has 2 dots on the other side. So the nitrogen over here has access to 2 dots and 3 dashes, and then the N on the right-hand side also has access to 2 dots and 3 dashes. So if we zoom back out and go look at the chart, each nitrogen has 2 dots, and it has, the dashes are bonds. Each of the nitrogens has 3 bonds, and those bonds count for 2 electrons. So we've got 6 electrons that are in bonds that the nitrogens have access to, and we've got 2 electrons that are lone pairs, so for a total of 8 electrons. And if you look at the nitrogens on the other side over here, this nitrogen has a pair of dots. This nitrogen has a pair of dots. It has 2 dots, and it has 1, 2, 3 dashes, 1, 2, 3 dashes. So the nitrogen has access to 2 electrons that are lone pairs, and then 1, 2, 3 pairs of electrons, so 6 electrons that are in bonds. Same thing over here, 2 dots, 3 dashes, each dash counts for 2 electrons. Boom. So the nitrogen has access to 8 electrons. Now, if we look at the hydrogen over here has, in between each set of hydrogen, so I've got 6 hydrogens here, each hydrogen is touching 1 dash. So they have 0 dots and 1 dash, 1 set of bonds, for a total of 2 electrons, which makes sense because that first energy level of electrons can only hold 2 electrons. So the hydrogen wants 1 bond. It wants 1 more electron, so forms 1 bond. So when you're doing your Lewis dot diagrams for like methane or something, and you've got carbon bonded to hydrogen, the hydrogen is going to make 1 bond with the carbon. The carbon has a place for 4 bonds, but the hydrogen can only make 1 bond. So you can't have hydrogen with 2 bonds. It doesn't do it. It doesn't work. It doesn't have the space, and it's not a big enough atom. The hydrogen, remember, is really just 1 proton in the nucleus for the most part. unless you're dealing with like deuterium or something, which we're not. Okay, so that's that. If we move on, we look at the next guy. I'm gonna give you some, I think you can get this done now. How do you feel? Do you feel like you can get it done? What are you eyeing, Lisa? You okay? Or am I moving around too much?
You're like my old math teacher. You're very
Yes.
fast.
I'm so sorry. I try so hard to slow down. What
It's
can
okay.
I will leave this. Let me see if I can make it small enough so you can see everything. There we go. So Avery, you want a screenshot? There it is, my man. Screenshot that action. Stone, I think you can probably stop recording. I think this is probably